In this part of the data structure course related to trees, we will cover some basic definitions on trees, then we will declare and implement a tree class for binary tree. Furthermore, we will cover in-order, pre-order and post-order traversal of a tree, which are all versions of the depth-first traversal. We will also cover breadth-first traversal, which is an alternative to the depth-first traversal. A tree is a set of nodes which is either null or with one node designated as the root and the remaining nodes partitioned into smaller trees called subtrees. Example, T1 is a tree which is null. This is a null tree. T2 is a tree having only one node. A is the root, the rest is null tree. T3 has node A as the root, and we have a subtree with node B. Under A, we have subtree B, and under B, we have C, and C has D as the subtree. And there is another node for B here, which is containing node E. And the other subtree under B is the subtree starting with node F. F has a subtree with root G, and G has subtrees with nodes H and I, and these subtrees doesn't have any more subtrees. So this is the graphical representation of T3. Here we have some definitions related to trees. The level of a node is the length of the path from the root to that node. The depth of a tree is the maximum level of any node in the tree. The degree of a node is the number of partitions in the subtree which has that node as the root. Nodes with degree 0 are called leaves. Consider this tree. The node A is in level 0, B in level 1, C, E, and F are level 2, D and G are at level 3, H and I are at level 4. So the depth of this tree, we are considering all the nodes and their levels. The maximum is 4, so depth is 4 for this tree. The degree of A is 1. There is only one subtree for which A is the root. The degree of B is 3. It has 3 subtrees. And degree of E is 0. There is no subtree for which E is the root. The leaves are E, D, H, and I. The degrees for these nodes are all 0. A binary tree is a tree in which the maximum degree of any node is 2. This is an example of a binary tree, and notice that for any node we have at most 2 subtrees. A binary tree may contain up to 2 to the power n nodes at level n. A complete binary tree of depth n has 2 to the power k nodes at levels k from 0 up to n-1, and all leaf nodes at level n occupy leftmost positions. If level n has 2 to the power n nodes as well, then the complete binary tree is a full tree. If all nodes have degree 1, the tree is degenerate tree or simply linked list. For example, a degenerate tree of depth has 6 nodes. A full tree of depth 3 has 1 node in the level 0, 2 nodes at the level 1, 4 nodes at the level 2, and 8 nodes at the level 3. So totally it has 15 nodes. A full tree of depth n has 2 to the power n plus 1 minus 1 nodes. A complete tree of depth n has nodes between 2 to the power n minus 1 and 2 to the power n plus 1 minus 1 nodes. As an exercise, find out what is the depth of a complete tree with m nodes. In the data structure representation of a binary tree, we have nodes in which the data is stored, and we have two link fields which are left and right. This shows the left subtree and the right subtree. If there is no subtree, the link field is set to nil. And we have a pointer which is pointing to the root of the tree. So if this is an example binary tree, we have the root A, then B and C are subtrees of A. B has no subtree and C has a single subtree having information D. And the corresponding nodes are like that. The root contains data A, and the left field points to a node containing data B, and the right link points to another node having data C. The right field of the node having data C is null, and the left one points to a node having data D, which has no subtrees. And also for B, we don't have any subtrees. The link fields are null. This is the template declaration of the tree-node class. In the private part, we have the link fields left and right, which are pointers to the tree-node of type T nodes. In the public part, we have data of type T. This is the constructor having the same name with class. And we have parameters item to be stored in the data field. We have pointer LPTR, which is a pointer to tree node initialized with null, and also RPTR, which is initialized to null, and it's a pointer to tree node of type D. If no data is provided for the link fields given here, their value will be null by default. We have access methods for the pointer fields, which are tree node pointer. This is the return value. The name of the method is left. There is no input here. It's a constant method. And similar for the method right. It's a constant method. There is no input. And it returns the right field of the node. Notice that data is public. Because of that, there is no need to write methods for getting data or storing data, which may be accessed directly outside of the class. Here is the implementation for the constructor. It is implemented as a template method. This is the name of the constructor, tree node, same as the class. It is a method for the class tree node of type T. We have item, LPTR, and RPTR as the parameters mentioned. Data is loaded with the value of item. LPTR is loaded to the left field, and RPTR is loaded to the right field of the node just created by the constructor. You may implement yourself the other methods declared in the tree node class. Similar to the get node for the node class for the linked list previously, here we have a function. This is not a method, but it's a function outside of the tree node class, and this function dynamically allocate memory for a new object. It is written as a template function, template class T. The name of the function is getTreeNode. It returns a pointer of type 3 node of type T, and we have three parameters which are item of type T, LPTR, pointer to 3 node, default value is null, and RPTR, a pointer to 3 node, again default value is null. Here a pointer of 3 node of type T is declared, and then by the new operation a 3 node of type T is dynamically created, for which the data is set to item and left is set to LPTR and right is set to RPTR. And the address of the new node is loaded to P. If P is null, that means that the new operation applied here is unsuccessful. In that case, the message memory allocation failure is sent to the error device and it goes to the next line and exits the program. Otherwise, if it is successful, then the address of the node just created is returned from the function getThreeNode. Here there is an example which uses getThreeNode function. First, a pointer T, which is a pointer to 3-node character type, is declared. So the nodes will contain data of type character. Here we are calling the getThreeNode function. So a node will be created and its address is going to be loaded into pointer T. Here the data provided is A, so a node having data A will be created by the getThreeNode dynamically. For this node, for the left field, getThreeNode is called. This time data is B, and for this node, the left field is null. There is no subtree for B. And for the right link, we have getThreeNode C. So another node is created here, and its data is C. Its address is loaded as the right field of the node with data B. And for the right field of node A, again we have getThreeNode, which creates a node with data D, for which we have here getThreeNode again to create a node with data E. Because no data is provided for the left and right fields, so E is created with null value in the left and right fields. And also no link is provided for the right field of the node having data D, so there is no right subtree. Here there is a function to deallocate memory. It's a template function. The name of the function is freeThreeNode. For each node created by getThreeNode, we are going to run freeThreeNode to remove it from the memory. freeThreeNode deallocates the node which is pointed by the pointer P, which is a pointer to 3-node of type T. The operation is only delete P, so the object, which is a 3-node pointed by P, is removed from the memory. We have 3 traversal algorithms to visit each node in the tree. First, we will consider depth-first traversal algorithms, which are in-order traversal, pre-order traversal, and post-order traversal. In the in-order traversal, recursively, we traverse left subtree, then we visit the node, that is, we process the information stored in the node, or we can apply some operation on the node, and then traverse right subtree. In the pre-order traversal, we visit node first, and then we traverse left subtree and traverse right subtree. In the post-order traversal, we traverse left and right subtrees, and then we visit the node. Here is the implementation of the Inorder traversal on a tree pointed by T. T is a pointer to the root of the tree, and it is of type tree node T pointer. If T is not null, then call Inorder. It is calling recursively the function itself with the left field of the node pointed by T. So this is to traverse the left subtree. Here we have cout. This is corresponding to the visit node step in the Inorder traversal, and the data field of the node pointed by T is sent to the output device at this step. And then we have a call recursively to the function itself with right field of the node pointed by T. Notice that here we are starting with the pointer to the root. If that pointer is not null, that means that we have some nodes in the tree. Here we are calling the Inorder with left. That means that we are going to traverse the left subtree. For the left subtree, now here T is the pointer pointing to the root of the left subtree. If T is not null, again it is calling the Inorder. So the left subtree of that node will be considered. So always the left subtree is visited here until we complete the left subtree, then the data is visited in the node. As an example, we are going to consider arithmetic expression tree, which stores operands in leaves and operators in non-leaf nodes. First, we will traverse the tree in Inorder traversal. That is, we will visit the left subtree first, then we will visit the node, and then the right subtree recursively. Here is the output produced by the Inorder traversal. Here in the visit node, the content of the data is outputted. Start with the root and first visit the left subtree. For this one, go to the left subtree, and for this node having value A, there is no left subtree, so the node is visited, and at the output we see A. Then return back to the parent node and visit the node, and we will see minus at the output. Then visit the right subtree. For this one, there is no left subtree, so the node is visited. We will see B at the output. And there is no right subtree, so this node is finished. We return back to the parent node because left subtree is visited, the node is visited, and the right subtree is visited. This part finished. We go back to the parent node. Because of that, the output we see plus as the data of the root. Then the right subtree will be visited in the Inorder traversal. We come to this node. For this one, we have to visit the left subtree. And from this node again, the left subtree is visited. Here we have the node having data C. There is no left subtree, so the data C is sent to output. There is no right subtree, so this part has finished. It returns back to the parent node, and slash is outputted when the node is visited. Then visit the right subtree. Here we will see D at the output. Then come back to the node because this subtree is covered. We return back to the parent node. We go to right subtree, from there to the left subtree, and then we will see E, then minus, and F in the Inorder traversal. So this is the output when the nodes are traversed in the Inorder traversal. If the code for the Inorder traversal is updated such that When a subtree is to be visited, we will have a left parenthesis, and when the visit of the subtree is completed, if we have right parenthesis, then we will have such parenthesis showing the order of execution for the in-order traversal. For the post-order traversal, we are visiting first left subtree, then right subtree, and then we are visiting the node itself. So if post-order traversal is applied on this expression tree, we start from this node and we visit the left subtree. From that one we visit the left subtree. Then we will see A at the output. And before the node itself, the right subtree should be visited, so we will see B at the output. Then comes to visit the node, so we will have minus there. And this subtree traversed completely. Then before the node, the right subtree should be traversed. For this right subtree, first the left subtree, so CD slash CD slash, and then EF minus will be sent to the output, and then comes this multiplication, and then we will have plus at the output. For the pre-order traversal, we will have visit order, first visit the node, then left subtree, and then right subtree. So at the output, we will see plus, then minus, then A, then B, as shown here. Then we will have multiplication, division, CD, then minus, subtraction, E and F at the output. Note that post-order traversal with the following implementation of visit: if operand push, if operator pop two operands, calculate, and push result back. This corresponds to arithmetic expression evaluation. For this purpose, its tag is used. Up to now, we considered in-order, pre-order, and post-order traversal algorithms, which are all depth-first algorithms. Now we are going to consider level traverse algorithm, which is also called breadth first. In the algorithm, the first step is insert root node in queue. Then, while queue is not empty, remove front node from queue and visit it. Insert left child, insert right child into the queue. Here is the implementation of the level traverse algorithm in C++. It is implemented as a template function. Template class is T. Here we have a pointer T, which points to a tree node of type T. There is no return value. Inside the function, a queue of pointers is declared. The name of the queue is queue as given here. Then a pointer P, which is a pointer to tree node of type T, is declared. First, we insert the pointer T into the queue by the queue insert operation. Here T is the parameter. Then in a while loop, while queue is not empty, we are deleting the front item from the queue by the queue delete operation on the queue. It is stored in the pointer P. And then we visit the data of the node pointed by P. Then we check if the left pointer is null or not. If it is null, it is inserted into the queue. And also the right pointer is checked. And if it is not null, it is inserted into the queue. This is the level scan algorithm. And let's trace the breadth first algorithm on an example tree. Here we have a tree. We have root at level 0. Then we have one node at level 1. Here is the level 2, etc. If we traverse, first A is visited, then B, then C, F, D, E, G, H, I. At the output, we will see this sequence. This is the level traversal of the tree.